So, welcome everybody. Is it too loud? Is it loud enough? Perfect. A little louder. So, my name is Michael. I'm a sociologist, and the funny thing is that I'm going to defend Homo Economicus. I'm not saying that the Homo Socialis is wrong and it's not relevant. I actually myself did a lot of research on this, on social preferences. But as a sociologist, I think let's start with that before we do that. Or let's be very careful when we focus on the Homo Socialis. Let's start with an example. This is a question. These are the kinds of questions we're having here. Why is that guy so evil? So I mean him, not the dog. And what would an economist argue? He would say, yeah, because he can do it and it's good for him. What would a psychologist argue? These are just stereotypes. They're maybe true. Okay, they're true. But it is stereotypes. A psychologist would argue, that guy is just mental. There's something wrong in his brain. And what would a sociologist say? Any guesses?
Society made.
Exactly. It's a social environment. That poor guy had an older brother that always beat him up. And he went to the KGB, and there he learned that being evil is the best thing to do. The right thing to do. Not a dictator. Why is that guy so nice? And now we come to the question of social preferences. An economist would say, yeah, in some way this must pay off in the long run. A psychologist would say, yeah, this guy has some personality characteristics that make him behave nice. Or we could call this, he has social preferences. So what economists do these days, they add to this explanation the kind of psychological concepts. And a sociologist would say, it's society that made him be nice. This is Emil Durkheim, the founder of sociology, one of our founding fathers. He was the first professor of sociology. And he had to explain to basically anyone in the world why we need sociology. And the question is not easy to explain. So we already had theories of individual behavior. Why do we need an additional field that studies groups and societies? And this is his answer. It's not new, it was not new these days, but he used it. He says, the whole does not equal the sum of its parts. So even if you understand all individuals, if you have a theory of all individual behavior, you may not be able to explain collective behavior, what groups do, what societies do. The whole does not equal the sum of its parts. It's something different, whose properties differ from those displayed by the parts from which it is formed. This is just an example. Here you see a map of New York. So this is Manhattan here. And the colors show you the composition of the neighborhoods. So I think this yellow represents that there are more than 75% white people. Green means more than 70% black people. So here in Queens, it's extremely black-dominated. Manhattan is white-dominated. If you just see that macro pattern, you would say, oh, this country is full of racists. You see that pattern, you see individuals' behavior, and you would conclude, yeah, that's what I want. That's what a psychologist would do. He would just say there must be something in their brains, in this case racism, that makes them create that pattern. But there is another explanation that was developed by Thomas Schelling, an economist. He made a very simple model. He just assumed that there's kind of a checkerboard, as you can see here, and I put there, I don't know, 10,000 agents, individuals. They have different colors, so they can be blue or orange, and I randomly placed them there.
Are you sure he was an economist? He was in the political science department.
Yeah, but he got a Nobel Prize in economics.
But he wasn't sort of the economy.
I agree. No. I'm not sure what he would call himself. I mean, he developed game theoretical rational choice explanations. His bargaining work is very economic.
Yeah.
I think he's one of the best sociologists, actually.
Well, I think he's a political scientist. He got his degree in that.
And this is also the field where he comes from, policy making. Okay, he's a good guy. So let's assume the following. Let's assume that these individuals here are very nice. They are not racists, but they prefer to live in a neighborhood where they are not in the vast minority. So they tolerate living in an environment where 70% of their neighbors are different. But if more than 70% of their neighbors are of the other kind, of the other color, then they move away. So they're extremely tolerant. And then see what happens. So the computer will now randomly pick one of the agents, check is that guy happy, are more or no, are even less than 30% of his neighbors of the same kind. If this guy is unhappy, the computer will just move the guy to a random spot, a random unoccupied spot. And what you will see is that from that random distribution at the outset, the whole population will segregate over time. Again, these guys here, they are extremely tolerant, but it's segregating. So you cannot explain the collective behavior based on the preferences only. In fact, there are extensions of this model that show that even if individuals get the highest utility if they live in a mixed neighborhood, if everybody wants to live in a mixed neighborhood, even then you will find segregation. Okay, so this is what the sociologists argue. Sometimes explanations that, theories that explain certain patterns that we observe just with the preferences may not be correct. This does not say that preferences, like social preferences, are not relevant and that they don't exist. But the sociologists are just not interested in that, because sometimes the whole is more than that. And this is what sociologists study. So what would a sociologist say? How can we explain, for instance, this pattern here, that we see segregation emerging? I just showed the movie again. A sociologist, so the explanation of what happens is that sometimes an agent is unhappy and then he moves to another neighborhood. That has two consequences. First, he decreases the number of his group in his neighborhood, which might make other neighbors of his kind also unhappy and also move away. Plus, he is going to move to a neighborhood where the number of his kind is increasing, which might make this neighborhood not nice for people who have the other group, who are from the other group. The interesting thing with that is, it's not in the assumptions. All the assumptions you make here is that pick an agent, move him away if he's not happy, and move him to a random spot. But to understand how this pattern of segregation emerges, you need to understand the mechanism that is triggered by these individual decisions. So this is the big thing that most sociologists want to study. It's the mechanism that leads to, that in addition to the preferences, lead to collective behavior. I very much agree with that, but in this talk I will talk about another ingredient, and this is randomness. The idea is that sometimes individuals follow certain rules. It might be irrational decision making, might be some simple rule they learned, but sometimes they also deviate from that. Nobody's perfect. People make mistakes, they misperceive situations, they have a trembling hand, they make wrong decisions. Sometimes they even try out another behavior. It's just trial and error. It can also be just trial and error behavior. And even though this is maybe completely unsystematic, it could be that very few of these deviations can have an effect on my neighbor, and this is his reaction to that has an effect on his neighbor and on his neighbor. And that way, random deviations can cause a cascade that changes to a big change on the macro level. This whole idea is not new. For instance, in physics, people study such cascades. What you will see here is, now is a little movie. In this bottle, there is something that is called supercooled water. It's water that is below zero, so it should be freezing, it should be frozen, but it's not frozen yet. It's liquid. I'll just show you the movie. So first, this person shows you that it's still liquid, so you see some bubbles. And he frozen on the ground, and you see that suddenly it started freezing here, and then this cascade is going through the whole bottle. And now it's frozen. Second example, still. Now he created a deviation here, you perturb the system slightly, and you see this cascade going. Question is, do we sometimes find similar things in human societies, human populations? And this is what we wanted to test, and we conducted an experiment to test this. So I will now go through each of the conditions of the experiment step by step. I will not explain the whole experiment from the beginning on. I will go through the conditions and explain for each of the conditions what our research question was. This is a photo from our lab. You see that these individuals, it's the desk here in Zurich. People sit in these cubicles that don't see what the others do. All the information they get is on the computers. Our question was, the question we wanted to test is, can deviations on the micro level have a critical impact on what we see on the collective level? This is the game the individuals played. So we invited groups of 20 participants to the lab, and each of them was then assigned a random position in this network. So some were dogs, some were cats. We did not call them cats and dogs, this is just for the presentation. Everybody had this position, and everybody had 4 neighbors, 2 to the right and 2 to the left. In this case, it means that every dog had 2 cats and 2 dogs as neighbors. Neighbors means that you were informed about what these 4 individuals did in the previous round. Plus, what they did had an impact on how much money you got. Pair rule was very simple. They played a game where we asked them, choose between 2 colors, yellow and blue. And we now use red and blue for graphical reasons only. So they always had 2 options, yellow and blue. And they got 1 point, which was worth money in the end, if a dog chose yellow, and a cat got 1 point if it chose blue. And now switch to red and blue. You can see that it's not nice to see the yellow thing. So a dog got 1 point if he chose red, and a cat got 1 point if she chose blue. Plus, everybody got 1 point for each neighbor that did the same thing. It's kind of a battle of sexes in a network. So that's the game. What we observed, and also what we tried to impose in this experiment, is that individuals used the so-called best response rule. The best response rule means you see what the others did in the previous round, and you choose the color that maximizes your payoff, assuming that the others are going to do the same thing again. It's an amazing theory for our experiment because 96% of the individuals actually did that. So the experiment was designed in a way that you can always say whether a certain choice was the best response or not. And the remaining little more than 4% were deviations from the best response rule. So what we could use, we could just use a standard model from the literature to predict what individuals do, and then also to predict what will happen on the macro level. This is the model. This function, the physicists call it a Fermi function, and the social sciences it's called a logit function. Basically looks like this. The main independent variable is the payoff difference between the 2 color options. And we have this parameter in it, this beta parameter here, which is sometimes called the responsiveness to rationality. If this takes the value 0, then your probability of choosing blue, which is shown here, is basically completely independent of the payoff difference between the 2 options. But if we increase this responsiveness to rationality, then you can see that the higher the utility is of choosing blue compared to choosing red, the more likely you're going to choose blue, and the other way around. So that's our micro model. What's going to happen? So first condition of the experiment, it's exactly the network I just described. Dogs get 1 point for choosing red, plus 1 point for each neighbor that chooses the same thing, and cats the same for color blue. We expected it at the very beginning, when the individuals play that game for the first time, and they have 0 information about what the others did before, because there was no before, that they would just choose the color that gives them that point. So we expected that the dogs choose red and the cats blue, and about 80% of the individuals actually did that. The interesting thing is this is an equilibrium. So imagine you're this dog. And you observe that in the very first round, your neighbors, you have two neighbors, you don't know their types, you don't know their utility function, you don't know anything about them. Everything you know is that in the previous round, there were two guys who chose blue and two guys who chose red. You're a dog, so you get 1 point for choosing red, and you expect to get another 2 points from the other two red guys. So you expect to get 3 points if you choose red. If you switch to blue, you will get only 2 points. So the rational decision is the best response is to stick to your color. This is completely symmetric, so everybody will stick to the color. We call this pattern anomy. But what happens if that dog makes a mistake? He's stupid, he doesn't think carefully. For some reason he chooses the wrong color and he switches to blue. In the next round he will immediately switch back. This is the rational decision. Also, these two guys will not change their behavior. They are very happy that there's actually another neighbor who's now choosing their color. But these two dogs, something changes for them. They now have 1, 2, 3 blue neighbors. So they get 3 points for switching to blue. And they get only 2 points, 1 because they are red, they are a dog, and 1 because they have another neighbor. They get only 2 points if they stick to red. So what they will do is they will switch colors. You see? Now, this dog and this dog are in exactly the same situation as the other two dogs before. They will switch color, and you see that there is a cascade starting that is moving along the circle. And now let's include here another deviation. That dog also makes a mistake. And suddenly the cascade moves in the opposite direction. And after 8 periods, the system moved from this equilibrium to a completely different equilibrium. There were 160 decisions made by the 20 actors and only 2 deviations. And this was enough to move the system from one equilibrium to another one. Of course, this is a constructed example. This is very important if you do study the whole system analytically.
Yeah, how many deviations will it take to move it back or move it to another one?
This is a stochastically much more stable equilibrium. It's much more stable. I would use this terminology in a minute.
I think 6 is the answer.
It depends when they happen. If they happen at the same time, I think it's 6. But you know, this is a case where deviations, I chose this case to show here because the deviations happen at different time steps and at very different places in the network. So you have many, many combinations of deviation patterns that can lead to system shifts. Just to show you that this is robust, what I show here, you again see the cats and dogs. They start in this anomy system, which is an equilibrium, and now they make mistakes based on this logit function. And you will see that it doesn't take long until they coordinate on one color. In this case, it happens to be red. So, this is what we tested. A theory that does exclude deviations, they always choose the best response, expects that they stay in this anomic equilibrium. A theory that includes deviations predicts coordination. So our question was for the lab, what are we going to find? This is a different visualization. This is what the deterministic model predicts, the one without deviations. Here you see time, they played this 150 times. They were really quick in the lab, it took them about an hour. Here you see the 20 individuals. And if they start with the color they prefer, then the deterministic model predicts that they will do that forever. If you include random deviations, and this is represented by these dots, you see that they start with anomy, and it doesn't take long until they coordinate. And this is what we find in the lab. You see again, at the beginning they start with this anomy pattern, and then there are these deviations, and very quickly they coordinate. And I hope this is interesting for you. We find many deviations also afterwards, but it remains stable. And I chose here just one session, did it of course many times. Not too many times because there are already 20 individuals, so this is really expensive, this experiment. I think we replicated this 4 times per condition. And we always find that. And I show you one with many deviations. So, deviations can have this important effect. But do they always have this effect? And even more important, if they do not always have this effect, can we predict when it has effects? This is what we studied with our second condition. Everything we changed was that they do not get 1 point if they choose the color that corresponds to their type, but 3. So dogs get 3 points if they choose blue, and cats get 3 points. No, dogs get 3 points for red and cats 3 points for blue. And let's again assume that that guy makes a mistake. What's going to happen? Of course, it's great for them, they get another point. And now this dog, he gets 3 points for choosing red, and another one from his friend, so 4. If he switched to blue, he would get only 1, 2, 3 points. So the best response is now to stick to red. This system is stochastically more stable, in the sense that a deviation will not trigger off a cascade. So the prediction now is the model without deviation predicts anomaly, so it's still the same game as before, and a model with deviations predicts the same thing. This is what we find. Again, you see that the deviations don't have a big effect. This is what we see in the lab. Both theories are correct. So what does that mean? Deviations can have these effects, but they don't always have these effects. And this cool thing, we can predict when. This is powerful.
Is it an equilibrium? Is the all red, all blue an equilibrium?
Yeah.
In
that
this
coordinated states are stochastically much more stable equilibrium than the other.
Even in this case with the 3?
Oh, here it's even more. Oh, yeah. No, even in this case it's less stable. It's
weak,
less stable
right?
than the other one.
It must be very weak.
No, it's not very weak. You need. I don't have the numbers, but you need much more than 2 deviations, which I remember. Okay, so we've seen that the model with deviations is making the better predictions. But we also observed some patterns in the deviation. So for instance, that red guy, he should have switched pretty quickly to blue, but he insisted on red. And actually this was pretty smart, because then the whole system moved to red, so he didn't lose points in the long run. Or look at that guy. He's a blue guy, so he's a cat. And at that moment, this is not 0, this is something like period 30. The whole system had moved to red, and it looks as if he systematically tried to move the system to the other state. Or that guy, he really wanted the system to return to the red phase. He tried hard, but then he gave up. Or look at this. This also looks very systematic. It could be random, but it looks so systematic. There is a guy who makes a deviation, and that guy sees the change in the behavior, and he's reacting to that. This is kind of an error cascade. Someone makes an error, or a deviation. It must not be an error. It could be a smart thing to do. He deviates, and this triggers a deviation of another person. So we were asking ourselves, is it perhaps problematic sometimes that these patterns occur? Our model assumes that these things are just based, that deviations are more likely if they imply more costs. So if they're very expensive, you will hardly see them. But there are other patterns, and could that be a problem? So far it has not been a problem, but we thought about creating an experimental condition where actually we expected to observe systematic deviations from the best response rule, and the question was, will this change the predictions of the model, or the outcome of the dynamics? Still, exactly the same experimental setup. Everything we changed was the network. Now, all the nodes, all the individuals were not connected to the 2 guys to the right and to the left, but they were connected to the next neighbor to the right and to the left, and to the one at distance 3. So that dog was connected to this cat, this cat, this cat, and this cat. You see that all dogs were connected to 4 cats and all cats to 4 dogs. Again, they had no idea about the network. They were not informed about the network. We only showed them the colors that 4 guys in that room chose in the previous round. So what's going to happen? Again, they started with such a pattern. What is this dog going to do? He sees that he gets 1 point if he sticks to red, plus he will get 0 points from his neighbors. If he switches to blue, he expects to get 1, 2, 3, 4 points. So what is he going to do? He's going to switch to blue. You see that? Everybody's in exactly the same situation. So what are the cats going to do? They're also going to switch to red in that case. So everybody's changing behavior. The next round, they're in exactly the same situation as before. The only difference is that switching their behavior again will also promise them another payoff of 1. So in this situation, if there's no noise, they will constantly switch back and forth. We call this pattern oscillation. And the interesting thing is that, it's not the interesting thing, but if you include random deviations, this is going to be stable. But wait, so there's a reason why we wanted this, why we were interested in this oscillation pattern. Assume you're in this oscillation pattern, so all your neighbors are constantly switching their colors. In that case, the best response rule doesn't make sense, because the best response assumes that the others will stick to their previous behavior. So as soon as these individuals realize that there's this oscillation pattern, they should systematically deviate from that best response rule. And our question was, do systematic deviations perhaps lead to different outcomes? And this is what we find. Again, this is the prediction of the deterministic model. So this oscillation pattern will be stable. I think it's difficult to see. It's just too much information for now. If you include deviations, as we showed here in an example, it's going to be stable. And this is what we see in the lab. It's completely different. They start with this enemy pattern, and then there are some deviations, but actually they so quickly coordinated on the color blue here that we could not even use statistical tools to find out what strategy they used at that moment. And again, we found that in all of our applications. Again, we had also a condition where we changed the payoff for choosing the color that corresponds to a type from 1 to 3. What is interesting in that one is, again, the deterministic model predicts this oscillation pattern. It's still the same game. But if you include noise, it will sooner or later move to a coordinated state again. But this is also not stable. You just have to wait a little and it will move back to the oscillation pattern. And this is an interesting thing. In only 150 iterations, you will find these constant phase transitions from one system state to the other. So we also tested that in the lab. What we find is, again, they start with the oscillation pattern. They really very quickly leave that phase, and they coordinate. And then there's that guy. He makes that's a deviation here, and this motivates his neighbor to also deviate. And that is enough to convince the 4 neighbors of that guy to also switch color. Thing is the following: if you are someone who prefers red. Now, if you have 4 neighbors who prefer red, and you suddenly switch to red, they will immediately also do that. Because they get 3 points for choosing red, plus another one from you, so it's 4. If they stick to their color, they will get only 3. And that way, some deviations can have a big impact on your neighbors, on your neighborhood, and the whole system is again not stochastically stable. And actually, we find it in one of our experimental runs that exactly this happens. So this coordinated system is not stochastically stable. I'm not going to talk about this. So we also, of course, did our test on the macro level. Again, what we find is that our model with that includes the deviations makes better predictions. Makes better predictions. However, in situations where we have this oscillation pattern, both theories suck. Both are really bad. Okay. I still have some time to go into that. So this is a secondary analysis of this data that I conducted together with Heinrich. What we tried to find out here is what is a good model of deviations. So if deviations have this big effect, we want to have a theory of that. We want to know how to include it into our models. And there are different candidates for that. One would be just that there is a constant error rate. You always have the same chance of making a deviation. Another one is the logit model. That's the one that we use. So that deviations are more likely when they imply small costs. However, if deviating would cost you a lot of money, you hardly deviate. It's this logit function. And then there are also ideas from theories of learning. For instance, it's argued that if you for some reason lose money, there's a payoff drop, then there's a higher probability of deviating. It could be that you're unhappy, or you think, oh, this might happen again, so I start exploring. could also be that if you see others changing their color, something is happening, there's also a higher chance of deviation. There are theoretical models that make these assumptions, and we wanted to test whether we find that in our experimental data. So, it's a regression model. What you can know, 4 regression models that we estimated. Logistic regression models where the dependent variable was, do the individuals make a mistake, deviate or not? 1 means that they deviate, 0 means they don't. And if you just include a constant there, you will find a negative parameter. And this basically, if you translate it into probabilities, just means that there's a 5% error chance. So the value I mentioned earlier. If you just include the deviation cost, so how costly it was to deviate at that very moment, you get a parameter of 1.5, and this is exactly the value that we used in our simulations that I showed earlier. And this is significant, so we do find very clearly that deviations are more likely when they imply small costs. So this really seems to be a very good model, based on our experiment. Then we included these variables from the learning theories, and we do find that payoff decrease in the previous period increases your chances of deviating. So if for some reason you lose money, someone changed his behavior or you changed your behavior, and your payoff decreases, there's a higher chance of deviating in the next round. Neighbor's behavior does not have this effect, but if I changed my behavior in the previous round, there's a higher probability that I will deviate now. So we do find, in addition to this important logit model that most of the theoretical analysis use, we find that there are other sources of deviations. But the important finding in general is that the logit function, this is the parameter 1.5 that we showed in the second model, really very nicely matches the deviations that we see. So here you see the payoff differences, so 7 means that if you chose red in the logit, you would lose 7 points. And in this case, we see very little guys who choose red, so very few deviations. But here, when the deviation costs are small, we see many more deviations. So this is a really strong model. Okay, there's some confusion. But still, these payoff decreases, and also whether I changed my behavior in the previous round, has a strong effect, and it is significant. You can see that here. So what we did is we had now only a look at those decisions of our individuals, of our participants, when they did not experience a payoff change, and when they did not change their behavior in the previous round, and when they did not experience a payoff decrease, and also for the other 3 conditions. And we wanted to see whether we still find the effect of, whether we still find this logit function, whether we still find that the costs play a role. And it basically is the case. So we always find, for all of these special cases, we find that there is this very nice logit function. So the logit model is powerful. It's a good model, but there's something more going on. And to make good macro predictions, we sometimes may have to include these additional sources of deviations. That's something for future theoretical work. Okay, let me wrap up. So this is the take-home message slide for the sociologists. Even in microtheory, it is extremely good. So our microtheory, the best response model, can explain 96%, 96. Yeah, it's 96. 96% of the individual's decisions. It's an extremely good model. Show me a model, a theory in the social sciences that can explain more than this. This is why it's so good to go to the lab. You can create a situation where you give them the individual so little information that they cannot use other decision rules. So it's a wonderful theory, but still it can make wrong predictions. Usually our theories can explain 10, 20, 30% of the behavior. But even if we can explain so much behavior, we are wrong. We can be wrong. And the crucial thing is we can predict under which conditions we make mistakes. We can predict under which conditions a system is stochastically unstable and move to another state. There are methods for that. And this is main thing for the sociologist. If you make deterministic assumptions, if you build your theory on only deterministic assumptions, then you don't make innocent assumptions. Actually, you might make a crucial mistake. It may not be exciting for you, but in sociology this would cause a debate. Okay, what do we learn about non-standard preferences, social preferences, other regarding preferences? I very much agree that these non-standard, other regarding preferences do change the predictions of our models, and we do see them in our empirical work. Nevertheless, sometimes we see individual behavior, like this in the Schelling model, or also in our experiment. We see that they are coordinating much more than deterministic theory would predict. You cannot always conclude that this is a consequence of the preferences. Sometimes there's more going on. In our experiment, it was that they were influenced by others, and there was noise. So, my recommendation would be, before we increase the complexity of our psychological model, of our decision theory, before we include more and more preferences, let's start with a much simpler thing and include noise. That could already do the job. And I make that point because first I do have some negative social preferences towards psychologists, because that's what they do. So they see something and their automatic reaction is, this guy must have wanted it. There must be something going on in his brain. But it could be the environment. And I see that more and more economists also adopt this strategy. The presentations, also in particular today, do not fall in that. So I very, very much admire your work, of course. But I do see more and more papers that study some aversion or some social preference. And it's not based on a theory, they just try it out. They will always find something. And there might be simpler ways to do it. Just have a Homo economicus model, add some noise, could do the job. And this is another message for sociologists, because in sociology the main method,
Just one question. So I think simpler models, okay, but why noise? Why is noise better than something else?
I'm not saying that it's better.
That's
But I'm saying before you throw all these preferences on your nice model, include a simple thing. That could do it. Test it. Actually, I would say the model with noise is the better baseline model. It's a fairer baseline model to compare your models of social preferences against. And I mean, you are very smart. You conduct these experiments where individuals, there cannot be cascades. So you completely exclude that. So all your results are completely unaffected by this. But what we typically argue is that we need these additional theories about assumptions about social preferences, because things we observe in the real world don't match our theoretical predictions. And my point is just, hey, it could be some cascade, it could be randomness.
Or in time, because otherwise I would like to make one remark.
We have 7 minutes. We know we have a lot of time, actually.
The point is, you can make a mistake also in the other way. You can also make a mistake in the other way. I think that one of the classical examples is public goods games. In the end, you have very little cooperation. An interpretation is, okay, at the end, they learn it. So the cascade leads to selfish behavior. But the underlying behavior is probably not selfishness, but conditional cooperation that creates that. So and then it's the question whether you, the cascade can not only help to explain behavior that you otherwise can't, but actually can also hide social preferences, so that you actually do not get the right model.
Agreed.
Because you have this cascade.
Agreed. Sociology is complex. And this is the reason why we are not performing well. That's the point of it. So, but I'm not a standard sociologist, because standard sociologists just do this questionnaire research. They do random samples, or they define some population they're interested in, and then they randomly pick people and interview them with questionnaires. And I believe that for sociology, this may be a fundamentally wrong approach. One problem is that if you have these random samples, you systematically assume a way that individuals might be influenced by others. You don't have that information in your data. You randomly pick someone and you assume that this guy is not influenced by others. There are some people, is Christoph here today? So there are people who use questionnaire techniques to measure networks. Who is connected to who is potentially influenced by whom, and in that way they try to disentangle psychological effects from social influence effects. So that's possible. But with random samples, you just completely assume that away. That's a stupid thing. Sociologists shouldn't do that. Unless you have a question where social influence is not interesting for you. But there's another thing. I argued and I tried to show that noise is important. If you do a random sample and then you do some regression, then all the deviations, all the randomness is put into the unexplained variance. You throw it away. But it could be that it's crucial. And sociologists are interested in macro effects. So if it's true that random deviations on the micro level have these important effects on the macro level, then just putting everything into the unexplained variance of your regression is wasting perhaps an important part of the whole story. Thanks.